Okay, guys, this is our next unit. I forget if this is lecture 10 or 11, but this is transformers and rectifiers. I separated them from the other circuit components because they're a little bit more complex to explain and understand. There's a lot going on with these. We invoke Faraday's law, Fleming's right-hand rule for electromagnets to understand transformers, and then there's different types of transformers. And then rectifiers, we're going to use diodes in a certain arrangement in order to rectify a big problem that we have. Okay. And that big problem will be revealed to you in short order. Okay. So again, we're talking about electrical components in the X-ray machine, the X-ray schematic. And we're going to talk about transformers, the transformer law, which is a math formula. It's just a proportion, don't panic. We're going to give you 3 out of the 4 variables. You just have to cross multiply and then do some division and you'll be fine. Okay. We'll talk about the function of a transformer, how Faraday, between Faraday and Fleming, we figure out what's happening and why we get a current on the other side. We are going to do some word problems with the transformer law. And so you will see those on upcoming quizzes and exams. And then we're going to talk about rectification and how rectification actually changes the electricity we're using such that we can more efficiently run the X-ray tube. Okay. So again, some of the circuit components we're going to see. I've covered some of these in the previous lecture. But this time we're going to look at the auto transformer, the step up and the step down transformers. In the circuit schematic, those are called the high tension or high voltage transformer for the step up transformer, and the filament transformer for the step down transformer. Then we'll take a look at the rectifier. The rectifier that you'll need to know would be the 4 diode diamond rectifier, which produces full wave rectification. And I think those are mentioned here because this is the default slide from chapter 4, but I've already talked about the induction motor, the rheostat, and solenoids and electromagnets in previous lectures. All right. So the transformer is utilized to increase or decrease voltage in a secondary circuit. Okay. It does this by Faraday's law of induction. It takes advantage of the transformer law. The transformer law will tell you how the voltage, or the alternate version of the transformer law, how the current is changing compared to the coils that you're using in your transformer. Okay, and so there's a mathematical relationship between the change in voltage and the change in the number of coils from primary to secondary side. So I know this picture only has 1 coil. Most transformers have 2 coils. The auto transformer, one version of it at least, has a single coil. Okay. And so the transformer capitalizes on Faraday's law. Well, what did Faraday's law say? Faraday's law said that when you push current through a coil, you'll create a magnetic field. Okay. Actually, that might have been Oersted. Okay. Faraday said a changing magnetic field will produce a current in a coil of wire. Okay. But Oersted said we can create a magnetic field with a coil of wire. So if we combine Oersted and Faraday's, not Oersted's and Faraday's laws together, and we have 2 coils close to one another, then we can actually induce current in a secondary coil. Okay? But if and only if that current, the stimulating current from the primary side, produces a changing magnetic field. Now, this is Fleming's right-hand rule for electromagnets, but that's with DC. You get a static magnetic field. If you connect a coil to a battery, you get a solenoid. You put an iron bar in the middle of the coil, you get an electromagnet. Static magnetic field, the thumb on your right hand, if your fingers are tracing the direction of current through the coil, either clockwise or counterclockwise, your thumb extended upwards will point to magnetic north. But this is DC. Let's run AC through a coil. Okay. And so if we have two coils, that's going to be called mutual induction. Alternating current supplied to the primary coil. And what's going to happen with your Fleming's right-hand rule if the current's constantly changing direction? So for a crest, just extend your right hand out and coil your fingers. Point your thumb upward and coil your fingers to like make a loose fist. Well, your fingers are coiled if you're looking down from above, counterclockwise on your right hand. And magnetic north is pointing up. But now that's through the crest. Now we're going to go through a trough. Okay? In a trough, remember the AC current changes direction. So you got to flip your hand over and curl your fingers clockwise. And now notice that your thumb is pointing down. Now keep flipping your hand over 60 times a second. Just kidding. You're going to sprain your wrist. Don't do that. But that's what's happening in the United States anyway. In Europe, it's 50 times a second, and you'll still sprain your wrist trying to emulate that. But the idea is you can become aware that magnetic north is changing position 60 times a second. And so you do indeed have a changing magnetic field. If you bring a second coil in close to that first coil that is powered by AC, the second coil will have an induced current in it by Faraday's law. By Lenz's law, that current will be in opposition to the stimulating current, the primary current. And so wherever you have a crest, you'll have a trough in the secondary current at the same moment in time. Okay? But that's a transformer in a nutshell. You power the first coil with alternating current. You create a changing magnetic field. The second coil experiences a changing magnetic field. And so there's an induced current formed in the secondary coil. By Lenz's law, that secondary current, the induced current, is in opposition to the primary current. All right. So nomenclature of these transformers. I mentioned the transformer law, which we're going to get to in just a second. Step up and step down refers to the type of voltage change you can expect through a transformer. Okay. And so my schematic symbols are always written like English sentences you read them left to right. So the left side coil in the top picture is the primary coil, and it has less turns than the secondary coil. And so we know that this is a step-up transformer because the number of coils increase on the secondary side relative to the primary side, so also the voltage will increase on the secondary side. So you'll get a higher output voltage for a step-up transformer. Compare that to the reversed scenario, the bottom picture. Now we have more coils on the primary side, the left-hand side coil, than the secondary side. There are less coils on the secondary side, the right-hand side coil of that bottom picture. Now we describe that transformer as a step-down transformer. Yes, if you take a step-up transformer and disconnect it from the circuit and flip it over and reconnect it, it is now a step-down transformer. Okay? And that's what I've done with this picture is I just flipped it over. All right. So remember I said 2 coils and current is induced in the secondary coil. But it turns out Faraday made no such distinction about you absolutely have to have 2 coils. And so what we get is this weird phenomenon called self-induction. If you just have a single coil, which is one of the versions of the autotransformer, both the secondary and the primary coil are one and the same, and both the impulse or stimulus current and the induced current exist in the coil. Okay, and so you can make bridge connections, either static connections. Just a second. Okay. So the constantly changing current polarity changes the magnetic field. And so we have a coil. Yes, even just one coil still experiences a changing magnetic field. And so Faraday says it makes no difference that there's no true secondary coil. You still have a coil of wire experiencing a changing magnetic field. And so connections on the primary side, the left-hand side of this single coil, act as the primary coil, and connections on the right-hand side of this single coil act as the secondary coil. Yeah, it breaks my brain too, but it totally works. Okay, and effectively, what we can do if we arrange it like I've got this diagram shown, where we have multi-point connections on the secondary side, we can effectively choose our output voltage by including or excluding coils on the secondary side. Okay, so if I move the multi-point selector switch up, then I'm going to get a higher output voltage. If I move it down, I'm going to include less coils in the secondary circuit, and I'm going to get a smaller output voltage. And so the autotransformer is utilization in the X-ray circuit is to select the kilovoltage. It's the KVP selector. Okay, and then just briefly, because the book mentions it, there's an inductive reactance. The coil acts as both transformer and resistor. Well, what that is the current. Remember how we said the currents were in opposition to each other? They do fight each other. And so you get higher resistance in the autotransformer than you would in a 2-coil transformer, in the single coil autotransformer, because the induced current is going to fight the stimulating current. All right. So our autotransformer has 2 primary designs. It can have 2 coils wired in series, or it can have a single coil on a single iron core and just connections and takeoffs. Okay. You will get more, I think you'll get more eddy current loss with 2 cores or 2 coils than just a single coil. Okay. For the schematic, you're probably going to see a single coil represented in the schematic. The primary side allows for line compensation because the electric company does not give us a static voltage. That's too fidgety for power transmission. And so they promise 110 plus or minus 10 volts. Okay. So what they really say is peak voltage will never exceed 120 in the United States. I'm not sure what they do in Europe, but peak voltage on your standard household circuit is 120. It's rated at 120. 120 being the highest it will ever get. It's really they aim for 110 plus or minus 10. And so sometimes you will get 120. Sometimes you'll get 100. So that's the best they can do, basically. If you want something more precise, you basically need a line compensator. Okay? And so the line compensator is not mentioned in the Carlton book. It's not mentioned specifically in the credentialing exam content outline. But it was a part of the schematic that I learned. I'm not sure if they'll ask about it anymore or not, but I'm going to teach it to you just in case. So when we get to the electric circuit lecture, I'll do a little bit of deeper dive on the line compensator. Okay. The output voltage for the auto transformer heads nearly directly to the high voltage or high tension transformer to be stepped up into kilovolts. So by selecting our output voltage on our auto transformer, we're effectively selecting kilovoltage across the X-ray tube. Okay, so the transformer law, this applies to all types of transformers. And so some of the problems you're going to see on the next slide don't deal with an auto transformer necessarily, but the transformer law holds for all types of transformers. And so it reads like this. It is a proportion. The voltage secondary to, oh, God bless, excuse me. Voltage secondary to the voltage primary is equal to the number of turns or coils of wire on the secondary coil versus the number of turns or coils of wire on the primary coil. Now for an auto transformer, it's the number of turns included between the connections, between the endpoint connections. Okay. So let's say I have an auto transformer hooked up to, you get two options with United States electrical grid, most electric companies. You can have a 220 voltage line or a 110 voltage line. And so we usually take the 220 because we got to ramp it up to kilovoltage anyway. So your X-ray machine is wired to 220. So that's VP, voltage primary, in your auto transformer. What do you say we put in 220 coils on our auto transformer single coil, and we connect to the very ends on the primary side? What does that do to this equation if I put 220 for voltage primary and 220 for number of turns primary? You see the mathematical magic there? You're dividing both sides of the equation by the exact same number. Any mathematician would tell you that's ridiculous. You're wasting your time. Just cancel both of those out. Multiply both sides of the equation by 220 and simplify the equation. And when you do that, you get voltage secondary, that is voltage output, is equal to number of turns secondary. So in the specific scenario where the auto transformer has the same exact number of turns as the incoming line voltage, then the transformer law reduces to the number of turns you select on the secondary side is the output voltage for the secondary side. And so that's how an auto transformer can be a KVP selector. Okay. So let's consider some transformer law problems. Okay. A step-up transformer has 500 turns on the primary winding with an incoming voltage of 120 volts AC. Okay. And so our number of turns primary, bottom right, is 500. Our voltage primary, bottom left, is 120. And then the voltage secondary, top left, is 600. How many turns on the secondary coil? Well, that's the unknown. That's top right. Okay. And so this becomes 500 times 600 is equal to 120 times x. Okay. So 500 times 600, that gives me 300,000, but now I need to divide by 120. And that leaves me with 2,500. So there are 2,500 coils on the secondary coil. All right, and then checking our answer, a step-up transformer, would that have more coils on the primary side or the secondary side? That should have more coils on the secondary side. So 500 increases to 2,500, so it fits the definition of a step-up transformer. It meets our understanding of the turns ratio. Yeah. So that is a correct solution, 2,500. Okay. A cell phone charger has a step-down transformer with 120 windings on the primary and 5 windings on the secondary. If it is supplied with 120 volts DC, what will be the output voltage? I'll give you about 5 seconds or so. Just set up your, I guess you might set up a proportion for that, or maybe not. Okay, those of you who are paying attention understand that transformers only work when you supply them with AC, and so your output voltage here is going to be 0 because you're supplying it with DC. Okay, so a little trick there. Okay, but if it's got 120 primary and 120 volts AC, if I change DC to AC, well, then the output, 5 over 120 equals x over 120. Well, x has to be 5. So if that was 120 AC, then the right answer would be 5 volts. But I was trying to assess whether or not you remembered if transformers were only powered by AC. What about the current change? And this is, the textbook is wrong. I hate to get on to, because I know it's tough work. I've tried to think about writing a textbook myself, and I realize what a difficult task that is, and how hard it is to organize your thoughts and your ideas and such. But so I don't mean to, the spirit of my criticism here is only to relieve the students from the error. I'm not really criticizing the brain power of the authors at all. They did a fantastic job on this textbook, but everything is see, and that's the rub in the teaching profession, is you don't really want to make any mistakes. You have to deliver perfect content day in, day out, and that is the pressure of any teacher who takes it seriously. Is the last thing you want to do is give your students bad information. Okay, so the reason the current change is inverse, now we might be saying the same thing now that I think about it, but it's not as intuitive going through Ohm's law as it is going through it's not intuitive going through Ohm's law as it is going through the power law. I think it's more intuitive in the power law. Okay, so let me bring you back to the power law. Power in watts is equal to the product of volts and amps. Volts, and I think you might remember this from before, was joules per coulomb, and then amps was coulombs per second. And so multiplying those two together, you get joules per second. It's energy divided by time. Power is a rate of energy consumption. That makes sense. That's what power is how much electrical energy, at what rate is the device consuming electrical energy. Okay. Well, power in a transformer, when you turn on the transformer, the energy of the input has to equal the energy of the output, because the time that you're operating the input is the same as the time you're operating the output. Okay. So let's say you're going to run the transformer for 5 seconds. You power up the primary coil for 5 seconds, and then you kill the power. How long was the secondary coil running? 5 seconds, right? And so the power going into the transformer has to be the same as the power going out of the transformer, because the time of the input time and the output time are the exact same. And so we get another equation where the denominators are canceling, you see? So the time that you run the input is the time you run the output. And so you can't have different energy numerators, because you're breaking the conservation of energy at that point. You can't have a device that you run for 5 seconds and you put in a certain amount of energy and you get more energy coming back. Well, except for an atomic bomb. Okay. And so in a transformer, the power law applied to a transformer means that if the voltage changes going through the transformer, the current has to change in the opposite direction to compensate, so that the energy in is the same as the energy out. The power in is the same as the power out. Now, there is some loss to eddy currents and heat and things of that nature. Okay. But in a perfect transformer, power in equals power out, so therefore voltage in is inversely proportional to amperage, or the voltage change rather is inversely proportional to the amperage change. Okay? So for that reason, current has to be an inverse change to voltage across a transformer. Okay? But we don't change the way we name them. Step up is always referring to the change in voltage. A step up transformer will step down current because it's inverse. You see? And I'll say that again slowly. When we classify these things as step up and step down, that's referring to the change in voltage. And then we don't name them according to the change in current. We just understand by this rule here and the conservation of energy and the power formula, both of those ideas combined, we need current will be reduced in the output of a step up transformer, because we can't break the conservation of energy. Okay. The book takes it through Ohm's law, which they're technically correct, but they don't offer an explanation, and the explanation it's a little bit more complex than this explanation. This explanation is dang near intuitive. Oh yeah, the time you run the transformer is the time you run the transformer. So the energy in has to be equal to the energy out. So the product of voltage and amperage in has to be equal to the product of voltage and amperage out. So if the voltage is increasing, the amperage has to decrease by the same factor. Okay. Transformer inefficiencies. Transformers have a 95% efficiency. Okay, that's because we've re-engineered them to be optimal. Okay, early transformers maybe not. If you just get like a nail or two nails and two coils of wire, you're not going to have a 95 and bridge them in close. You're not going to have a 95% efficient transformer. Modern constructed transformers have 95% efficiency. Okay. Three types of transformer loss. One is the resistance properties of copper. Okay. And so the copper coils have a natural resistance to them. Okay. Make the wires large enough diameter and you reduce the resistance. Okay. We can also, I don't think they cool them as much as they do insulate them, but I imagine you could cool a transformer too and increase the conductivity. Okay. Wonder if everyone's ever tried that. A superconducting transformer. I imagine somewhere someone has invented such a thing. Hysteresis loss. Hysteresis means that not all the iron atoms are going to be responding instantaneously. There's going to be some lag. And remember magnetic fields and domains. So each individual atom has to flip in the iron core. Okay. If we separate the iron atoms and thin them out with an inner space material, then they don't get as much lag. Okay? Isolated iron atoms embedded in silicon or isolated iron granules embedded in silicon flip a little bit faster than if it was a solid chunk of iron, because basically the magnetic fields interfere with the neighboring magnetic fields. So each iron atom has its own magnetic field, and it's basically going to do what its neighbors does. And so you'll get some that are, for whatever reason, because it is a quantum effect, are delayed in flipping, and so their neighbors will be delayed in flipping. And yeah, you'll have some domains that struggle to flip exactly at 60 hertz. Okay, if we space out the iron into tiny particles like iron dust in silicon, then we can reduce the number of neighbors, and then we can reduce the lag, reduce those stubborn domains. Okay, and then eddy current loss. Basically, you're going to create, every time you flip the magnetic field, you're going to create magnetic field tornadoes that kind of spin off. Okay, those are the eddy currents. If you laminate the cores, that is, put in more inner space, put in sheets of iron rather than solid iron, put non-magnetic material in between the silicon iron, and make them little rings or little plates, then you won't get gigantic magnetic field tornadoes. You'll get smaller. So you won't get F5s, you'll get like F1s. You'll still get eddy currents, but they'll be reduced. Okay. All right, so your structural classifications of transformers, air core is the least efficient. That's basically two solenoids in close proximity. Probably the cheapest to build. You could, if you're properly motivated, you could get yourself some conducting coil wire at your Home Depot or your Lowe's or whatever hardware store you prefer. and you could build yourself an air core transformer in short order. It would take you maybe 30 minutes. Okay. An open core transformer, stop by the carpentry aisle and get you some galvanized nails. And then you can transform your air core transformer to an open core transformer. So the first two types you can build on a desktop in less than an afternoon. Okay. Both of those types fairly inefficient. Our modern transformers are typically your closed core, which you're going to see on the diagrams, or your shell type transformers, which if your closed core is a box formation of iron laminate, your shell type is a cinder block formation of iron laminate. Okay. The closed core and the shell type, more expensive to build, more engineering in mind, more of those laminations and the silicon iron, so specialized materials. The shell type is the most efficient, but it's also the most expensive one to build of those. So A and B are definitely not used in any serious electronic device. All right. So it's your closed core and your shell types that are giving you 95% efficiency for your transformers. Now, rectifiers. So our transformer runs on AC. Our X-ray tube, though, does not like AC. Our X-ray tube, if we try to power our X-ray tube with AC, we end up burning up the components of our X-ray tube, notably the filament, way too fast. Okay. And so we can get more efficient X-ray production out of our X-ray tube and keep the components of the X-ray tube from taking excess damage if we somehow supply it with DC coming off of the high voltage transformer. So we have to correct the situation, or here in the South, rectify the situation. What is the situation? We have a high voltage transformer that is outputting high voltage AC, but we need to change that or rectify that into high voltage DC. And we do that with a rectifier bridge or just a rectifier. So the rectifier uses a geometric arrangement of diodes. Now, the more complex your rectifier diode arrangement is, the more complex your DC output wave is. And so this is just a full wave rectified DC output wave. If you're into three-phase 6 or three-phase 12, you need more than 4 diodes. I think you need 6 and 12. You don't have to learn the diode rectifier for the three-phase power. Okay, this is the diamond diode rectifier, or the 4 diode rectifier is the one you have to learn for the schematic. Okay, this is going to give you full wave rectified output voltage. Okay, so the green and the orange are the inputs from our secondary side of our high voltage transformer. And a handy exercise is to, hang on just a second. All right, so if we start with AC, a good exercise to do is to trace either electrons coming in from green or coming in from orange, and figure out, according to the diodes and the way current runs through the diodes, figure out where the electrons are going to end up. And you can go ahead and do that. So bring electrons coming in from green, and you'll see that they're only allowed, of those 2 diodes, they really can only go to the left. They're going to be stopped by the diode on the right because they're heading the wrong direction. So going to the left, then they're only going to be able to exit at the red. Okay? And so that's where we would like to connect to the cathode. Okay, but what about orange? Because it's AC. And so half the time the electrons are going to be coming from the orange. And so bring the electrons in from orange. And again, they can only go to the left. And they have to exit at red. And so no matter which way I push electrons into the ring, they have to exit at red. Well, what about positive charges? What if Ben Franklin was right? He wasn't, but anyway. All right, let's bring positive charges in from green. And you will see that positive charges have to go to the right and exit at blue. And let's bring the positive charges in from orange. And again, the positive charges have to go to the right and exit at blue. So what we have is AC input, but DC output. The positive charges always end up at blue. The negative charges always end up at red. And it's the diodes that are steering the traffic. Self-rectification. Before we figured this out, before we figured out diodes, we used to just wire the X-ray tube straight to the high voltage transformer. And what that meant was that the X-ray tube was actually stopping the electron flow when we ran the current in the wrong direction. Okay? The X-ray tube can totally do that, but what happens is that filament 60 times a second would become positively charged, then negatively charged, then positively charged, then negatively charged, then positively charged, then negatively charged. And so the filament in the cathode of the X-ray tube would effectively start acting like a transformer. And then it would self-induce and it would create eddy currents and heat loss because it's an open core, it's a filament. It's a coil of wire. There is no iron core at the filament. And so you inadvertently create a open core transformer at the cathode filament if you self-rectify. And what would happen would be the X-ray filaments would burn up. You would exceed the heat capacity of the fine wire used for the filament and it would just burn. It would melt. Okay? And then your tube would be ruined. Okay? And so, yes, the X-ray tube can stop the troughs from the electricity flowing the wrong direction. It won't work in an X-ray tube. Okay? But the consequence is your filament takes a lot of heat damage and ends up melting. The X-ray tube, and that's because the X-ray tube is a specialization of a Crookes tube. It's a re-engineered, souped-up Crookes tube designed to make X-rays, not necessarily create an open core transformer at the cathode filament. And so a self-rectified tube is not a thing. We know better now. That's just going to burn up your X-ray tube. So it's not really a thing. Theoretically, though, it did work for a little while, but you would keep having to replace your X-ray tubes because you always burned out your filaments. The efficiency of the X-ray production is not as good as doing something different than this, and so we don't do this anymore. Okay. So we always rectify. Okay. So when we first figured out rectification, we said we just need to stop the current from reaching the tube so we don't damage the tube. So the first version of rectification was half wave rectification, okay? Such that you would arrange the diodes so if the electrons weren't going to the cathode, they were trying to get to the anode, the diode would stop them. Okay? This was a vacuum tube rectifier, and we don't use vacuum tube rectifiers because those also burn up. But it's cheaper to replace vacuum tube rectifiers than it was to replace entire X-ray tubes. So vacuum tube rectifiers, half wave rectification just kills the circuit, kills the current if it's trying to flow the wrong direction to the X-ray tube. And we burn up the vacuum tube rather than burning up the X-ray tube. And so it's cheaper to replace the vacuum tube. And so that's just like circa 1930 or so. Okay. And then we developed semiconductor technology. God, I can't tell you when. I really should look that up. That's something a science nerd like me should know. But we replaced the vacuum tubes with PNN type doped silicon semiconductors. And they work like they work here. If we connect the power the correct way, then we get an exchange of extra valence electrons with holes in the middle at the junction, and current can flow. If we try to run the electricity through in the opposite direction, then we get separation of the valence electrons and the available holes, and there is no jumping across the junction and current doesn't flow. Okay. So half wave would be two diodes to guard current to guard positive charges from getting to the cathode and to guard negative charges from getting to the anode. Full wave rectification is safety, but also an improvement of efficiency. Okay? So this is half wave. Half wave output, basically you erase the troughs. You got 0 voltage when there should be a trough. Okay? So you still get a voltage across the X-ray tube during a crest. It's just during a trough, it's basically the circuit's dead. There is no electricity flowing. That's why those are dotted lines for troughs. The trough should be there, but it's being stopped by the diodes. Okay. This is inefficient because you're only using half the electricity effectively, and you're producing a pulsed X-ray beam. Now, you will see this is a much cheaper build, though. And so for some veterinary X-ray units still use half-wave rectifiers because it's a cheaper X-ray machine. Okay. And then I don't know about podiatrists using, they're probably using at least full wave. I can't imagine, but podiatrists would only be taking X-rays of the feet, and so you don't need necessarily efficiency of the X-ray machine and consistent high voltage. Really what we're talking about with the improvements of the voltage waveform, it's all about the spine and the torso. We want to be able to punch through the torso and X-ray the spine. All right. So our next, well, we killed the power for the troughs. What if we could use the troughs? What if we could flip them and invert them over the line? And this is what your 4-diode rectifier does. Is it basically inverts the troughs in your AC waves and makes them into additional crests. So a 60 hertz AC wave going through a 4-diode rectifier will produce 120 hertz DC. Hertz and DC, what? Yeah, it's pulsed DC. Okay, so you get crest instead of crest trough. So a full wave is crest now. Two crests make a full wave. Okay, so full wave rectification means we're utilizing the full wave. We're not using only the crests. We're using the troughs too because we've inverted them. Okay. So full wave it still takes into account safety, and we're not going to burn up our X-ray tube. We're not going to damage our X-ray tube, and we're going to use 100% of the AC wave to make the X-ray. So full wave rectification, it says most efficient form of current for X-ray production. Yeah, this is single phase still though. So three phase 6 and three phase 12 pulse are still more efficient than full wave single phase, which is what you see here. Okay. All modern equipment is technically full wave rectified, but we call it three phase 6 pulse or three phase 12 pulse. Both of those are also three wave rectified, but they use more complex rectifiers than just a 4 diode bridge rectifier. Okay. So basically I've taught you about transformers now, the three types of transformer. We're going to use an auto transformer, we're going to use a step up or high voltage transformer, and we're going to use a step down or filament transformer. Okay. And the circuit is divided into three main sections. The low voltage circuit, which is in the green, that's also called the control circuit because that's where the selections on the control console are located. They didn't include the timer circuit, but it's in there. Okay. The high voltage circuit, which I have divided the high voltage transformer because the primary side of the high voltage transformer is technically low voltage. And then the filament transformer, while it's not high voltage, it is dangerous. So it belongs in the high voltage circuit. Technically, it is in the same insulating oil bucket as the high voltage transformer. And I think the auto transformer, the high voltage transformer, and the filament circuit, as far as I know, they're all stacked in the generator in one bucket of dielectric insulating oil rather than three separate containers. Okay. Depends on manufacturer. They could totally separate these into their own buckets if they wanted to. But I think for efficiency's sake, they're all stacked in the same bucket. Okay. The filament circuit is outlined in the red. Some of that is obscured by the green line. I apologize. Notice that the cathode filament of the X-ray tube is in both the high voltage circuit and the filament circuit. Okay, and that's because it's got a bridge connection to the high voltage circuit. I'll go into a deeper dive into the piece parts. I've got my own an entirely different lecture for the piece parts, and I'm going to use a different schematic than this because I think this is oversimplified and it doesn't use the schematic symbols that I taught you. I think it's a mistake to not teach X-ray students the schematic symbols because they're going to use the schematic symbols on the credentialing exam. So if you get a question about this circuit, it's not going to be these pictograms like you see here. It's going to be electrician schematic symbols. Okay. So I understand the illustrator doesn't want to violate copyright, and that's probably why they took liberties and made and drew things a little bit differently here than they did in some of the other authors. But we have to teach the students schematic symbols because that's what they're going to encounter on the registry. So just a slight critique, not really a flaw. This is a working X-ray circuit, and It's exactly the same as the circuit diagrams in the other authors. More of a critique than an error. So, but yeah, your low voltage circuit is synonymous with a control circuit. Your high voltage circuit is also called the high voltage transformer circuit. I don't see the rectifier in here either, though, so that is a flaw. The rectifier should be in between the high voltage transformer and the X-ray tube. And then the filament circuit. There's some disagreement as to whether the rheostat. Some people say the rheostat is in the filament circuit as well. I'm in that camp. But some folks say that the rheostat is in the control console circuit. I don't know what to tell you there. I say it's in the filament circuit. So, but deeper dive on this complete schematic. Don't be scared of it. You already know all the components. You already know what each component does. I just got to put it all together in a nice little package, and that's what I'll be doing in that next lecture. All right. Now, thermionic emission, I'll be coming back to they mentioned this in chapter 4. I think it belongs in chapter 5, the X-ray tube. But the whole point of the filament circuit is, remember, it's got the step down transformer. And so the voltage is decreasing and the current's change is inverse to that. So it's increasing. We need a big current flowing through the filament so that we get excitation of filament electrons. And those electrons get to excited states. They raise up basically out of the valence states and the lower shells into a conductive state. Now they don't have anywhere to go until we apply the high voltage, and then they're yanked and accelerated toward the positively charged anode. We'll talk about that in chapter 5. The filament is heated to a high temperature and then breaking apart thermionic pertaining to ions by heat. Okay, so if you heat up wire, you'll get it to glow. The glowing is characteristic cascade because you're exciting electrons in the material of the wire, and then those electrons are relaxing back down and they're giving off heat and light when they do that. Okay. And so you see this with, if you have an electric stovetop, you see thermionic emission when you turn the burner up to high. That red, now typically in the modern ones, it's red LEDs, but in the old tungsten ceramic coils, it's literally the tungsten is glowing red hot because it's got excited electrons. Okay. The boiling off of the electrons around the filament in the X-ray tube creates a cloud of electrons. Loose, they're not really tethered to the filament wire atoms anymore. They're kind of available to run away if they wanted to. Okay. An incandescent light bulb basically relies on thermionic emission to run. Thermionic emission and a hot cathode filament is important to X-ray tube design because it makes, rather than a cold cathode, it makes more electrons available. Getting them up into the excited state makes them more available. They're at a closer energy state to full conduction where they can just leave. Okay. All right, and then after we learn the electric circuit and the X-ray tube, we'll be pivoting back to building your lightsabers. Okay. They blew up Jeddah, so we're going to have to find another source for kyber crystals. but I think the rest of the components we'll be able to buy down at the hardware store. Maybe the Diantium power cell might be tricky to get a hold of. Might have to deal with some unscrupulous people to get a hold of those power supplies, but the rest of the components um, we'll be able to fabricate these in short order. We just need some kyber crystals and some diatinum power cells. So I'll be working on getting those guys. All right. So yeah, electrical components for the X-ray machine. Between this lecture and the previous one, we have walked through all the circuit elements, is what I would call those things. Transformers and rectifiers, a little bit more complex, at least as far as what you need to understand the X-ray schematic inside the bounds of this course, and what you need to know for the registry. So, but I have already explained to you every piece, every circuit element that exists in the X-ray machine. Now it's just where do they appear in the schematic, and what job does it perform as far as ultimately getting to the goal of making X-rays. Okay. We talked about transformers, the various types, how they're named, both by how they're the design in which they're built, but also whether or not they are mutually inducting or self-inducting, and whether or not they're step up or step down. Okay. We worked with the transformer law with a couple example problems. You are going to see quiz and exam questions coming up with the transformer law. Transformer law is among one of the equations you might be asked about on the registry exam. So, and then we talked about rectification, and we traced electron flow through a 4-diode rectifier. We also traced Franklin current through the 4-diode rectifier, and you can see how it outputs a pulsed DC from a single phase AC wave. Okay. Which allows with that 4-diode rectifier, it allows us to utilize both the crest and the trough to push electrons from the cathode to the anode to make the X-rays. All right, I'll see you next time. I believe the next one is the X-ray circuit itself. So looking forward to that. Take care.